some of these groups
Sure.
in the community. So you're not only a college band playing for the college and the community, but you're also supportive of some of the nonprofit organizations that like to present little benefits.
Well, we last spring, our last concert of the year was done in conjunction with the Child Care Center here on campus. They're an organization that constantly is in need of funding and support, so we did a joint concert with them and gave them the proceeds.
Greetings. Today I am going to talk about the homework, so I hope I have a captive audience, at least those of you who did the homework. And I was the bottom line is that I was quite pleased with most of the solutions, and I learned something from it. I think maybe it might be mutual, and that we'll all have learned something from this. So there's a handout that do you have it here? Handout number 22 talks about it. So you can be reading that instead of looking on the screen. This was hot off the press. They were just hot off the Xerox machine just on my way to class. But I think it's probably not too many typos. The assignment, as you'll recall, was to take the exercise in Gilman's book, in the appendix of Gilman's book, which showed how to take a paper from before to after, where after had much simpler notation, and to use the same ideas again on after to get post after, or whatever the next term is, and something that goes once through even simpler notation. And so now we have a general unwritten law in our department that when we give an assignment, we should also try to work it ourselves before we ask the students to do it. Now, we don't always remember to do this, but it is definitely a policy, certainly on our exams that we set, the departmental exams, that we always have the answers prepared, that we think we can work the problems on the day that we give the assignment, and then when we publish answers later on, we also will improve them based on solutions that people actually did in the exams. But we're supposed to have worked the problems before we give them, and that has actually not always been the policy of the department, and it was introduced because of some surprising errors that occurred where people had completely unscaled their, they thought that the problem could be done in an hour, and it took a couple of weeks and things like that, and when they actually got to working on it. So anyway, I did the same with this homework assignment. I tried to solve it before I dared assign it to you, because I didn't know, unless I had gotten to the end of it, that it would actually be possible to go through and improve on Gilman's work at all. And so I present in solution 1 here the thing that I wrote out. In fact, I wrote this solution A the same day as I wrote the handout that you got assigning the homework. So when you saw the homework problem, Phyllis typed this also the same day. And so I had both of them sitting there in front of me, and this is just a rewrite, sort of follows sentence by sentence pretty much the way the other one was. And I don't want to read it to you now. You can read it at your leisure. But I want to point out something about that I did change in the theorem. That if you remember, the actual theorem had a more complicated property in it. It says it said if alpha and beta are unequal, then alpha is in A sub beta or beta is in A sub alpha, and I simplified that because I realized that it didn't matter. You don't have to have that property alpha unequal beta. You could just say for any alpha and beta this is true. Now the reason is, I've changed the theorem, so this was something that I'm not surprised other people would hesitate to do, because I didn't say change the theorem. But this theorem is simpler to prove, and it's equivalent to the other theorem. Because if you have a family which has this property for all alpha and beta, then it certainly has the property for all alpha unequal to beta. That's a weaker thing. On the other hand, if you have the weaker condition, then all you do is add alpha to A sub alpha for every set, and it works, and then this condition holds in general. And so you can always get from the weaker condition to the stronger condition. And so there was no point in cluttering up the proof and the hypothesis with this extra complication. So I simplified it in that way. But that was a minor point, but it's worth noting for those of you who got into this problem. The next thing is that I followed a general strategy in here that would apply to many other things, and that is I tried to avoid enumerating things when I didn't have to. So instead of saying that n is a sequence, n sub 1, n sub 2, n sub 3, I just said n is a countable set. So I didn't say it was a sequence, I just said it was a set. Then later on, when I needed to know it, I could talk about the kth element of it, or something like, of a countable set in some enumeration. But I didn't have to enumerate it until I needed it, and then I could just need it locally. And for one or two sentences, we had a subscript that was implied, but easier to understand, in fact, and having so many subscripts and superscripts all over the place. So that was the method I used here, and carrying it through, it gives a solution, as you see, and the factor of 2, I guess, in reduction of length. So although the argument was the same, essentially sentence by sentence, you can sort of map the old sentences into the new ones. They get shorter in this way. Now, what I didn't realize in this was that is a trick that most of you actually used in your homework papers, that you held back. You didn't hold back in the same way of not numbering the sequences, but you held back in not naming the correspondence with a notation. So here, in other words, I had a set corresponding to alpha is called n sub alpha. And a lot of you, in your solutions, you didn't do that. You just said, in the proof, let n be the set corresponding to alpha. And, you know, or you say, we will call this the corresponding set, or in fact, there was a better word in the counterpart, yeah. And that was a nice, you know, so it turned out to, you know, that was another way of holding back on introducing notation when you didn't need it. So I still was hung up on the idea of putting an alpha in this thing, and in this sequence that I named, I decided to call it alpha 1, alpha 2 in that way, instead of the way Gilman had done the other one. But I didn't need that. I could have just said C was the corresponding set to alpha. So anyway, this is my solution. However, I didn't rewrite it again after finding out the better ideas from you guys. Now, the one that I like best is solution B, of all the ones that were submitted, and this has three or four really nice aspects to it. So I want to emphasize them now in words, and then you can read them again after class. But here he just says, we'll call the sequence, we shall call, he says. It's okay, the guy got by me, I don't mind a shall. But you could call it the sequence of ordered pairs corresponding to alpha, the counterpart of alpha, and vice versa. Now, turns out counterpart is a nice word. Hasn't been abused for any other purpose in mathematics. So when you get to counterpart, you're going to be able to remember. It also has the right feeling for this problem. So when you get to the thing here, you can talk about the counterparts. Okay, now, so the other thing he did was in this lemma, he changed it from an ordered pair of sequences to sequences of ordered pairs. Now this is really the same thing. If you have two sequences, you know, those are two arrangements of numbers on a line, but there's also, it's a sequence of columns, each of which is an ordered pair. And now this was a seemingly minor change, but it actually meant that now you could think of the columns, the n sub l and the t sub l, as if they were just a pair, nt. And this is really like a function that maps n into t, that very natural. While the Sierpinski's proof had this very indirect. You had to go from n to t by knowing that n sub k was mapped into t sub k. Well, this is, Pang in his solution here discovered that really it was a mapping from n to t. So you think of it as an ordered pair rather than two sequences that are somehow going in parallel. So that was a nice way to cut through the logic of the argument and realize that. That I think was an excellent discovery. So what happens is that when you get this, once you make that change, then you can go through the theorem and actually come to a point where not only can you check it, but you can understand it. The theorem, you can sort of I don't know. The best way I could say as to what this accomplished was that the proof of the theorem is now factored into two parts, which have a simple interface between the parts. There's one part that you can understand in itself, and then you can understand the second part, and there's a simple connection between the two parts. And he explains that in his theorem, and he says that he first constructs a sequence of Fn with the property that for all alpha and for all beta and A alpha, there is an ordered pair Nt in the counterpart of beta with this property that relates Nt and alpha. So here he gets now this is sort of a lemma, a sub goal that goes between the theorem and the final proof, and this is the interface between the two halves of the proof. That's like taking a large computer programming and dividing it into modules that you can assign to two different programmers, and they don't have to know much about it, except they have to get to this, this sub goal, and you can get from there to the end. And the Sierpinski's proof and my write-up of the thing, everything was all one big muddle. I mean, not muddle, but it's on one page, but it's a bigger muddle. Everything was, you were doing both things together, a little bit of one, a little bit of the other, and so you had to keep more in mind. So this factoring is certainly an ease, a way to make the proof comprehensible. And then he says the construction is essentially a diagonalization technique. Now, anybody who's been working with countable and uncountable sets will know that Cantor introduced diagonalization technique to prove that sets were uncountable and so on. And so he's also relating this. He's sort of saying, here we're doing a diagonalization. He gives us a clue as to the structure of the proof, not specifically pointing out what he's diagonalizing, but just by this comment saying that it's essentially diagonalization is very helpful to provide the reader gives some confidence that he's going to be able to understand it, and to get sort of a feeling for the structure. So that's another nice thing. But the main idea was the factoring into this property, and then he reinforces the property at the end. He says, moreover, the sequence has the desired property. He repeats the property here, and we can now check it at this. And so we got the property stated twice. Now we could have, factored it out into two lemmas, lemma 1, lemma 2, and so on, but that wasn't probably necessary because you could do it in a paragraph. And then the second paragraph shows how having that property is the key to proving that S is countable and so on. So he gets through the whole idea, and you could now also apply some of the simplifications in solution A to make this a little simpler yet. But pretty much that's why I like this as the best solution. It's certainly, I agree with the grader who said that it was easier to understand his solution than to understand my solution to the problem. Okay, now I gave a solution C here, just excerpts of it, so these three dots mean, there's more going on here. And this was just to illustrate some of the better examples of the way many of you avoided the double subscripts just by, like here we say we call this the integer sequence of alpha, and you just call it the integer sequence of alpha, and you don't say it's capital, it's script n sub alpha or something. You just use English instead of symbols, and sometimes English is better than symbols. Symbols aren't always a win. Sometimes you got to have symbols because you got to have a peg on it, but holding back and not giving a name to that was a win here, and so the way that actually was achieved, and I give excerpts so that you can see what the central idea of that solution was, and many of you used that idea. And now solution D, I want to show you the original of that one, because this David Salison had presented us with two answers, like Wilf did when he gave us two extreme examples of how to write up a proof. So we have two proofs here. One is for the logicians, and one is for the people that what does it say? A more elaborated treatment meant to be understandable to someone like myself. And here I want to show you the illustrations, and you should look up there in color because. And I couldn't reproduce them in the handout because they're in 4 colors, and this is now if we had restricted this to a black and white thing, it would be interesting to see what he would have done. I mean, the directors in Hollywood were very resistant in 1930 to introducing color and sound into movies because they had developed a great art of how to communicate with black and white, and this was all being lost, they felt, as you went to movie. But color is certainly a very effective thing. You're going to make any brochures or something to boy, it sure doesn't. Well, when we focus up on it, you'll be able to get the idea here. But now. So I give the beginning of it in words, and there's 7 illustrations, and they build on each other in an interesting way. So that's what I'll get at here. But he starts out and he says, suppose we have a function spec of alpha that maps every real alpha to a countably infinite subset of the reals, figure A. So here he has alpha and is some element of the real line, and then he has spec of alpha, which is a countable set on a real line. Now this figure is like any illustration can be a bit misleading. A countable set doesn't have to consist of discrete points. They can have limit points. They can be all this, things that approach the square root of 2 or something like this. And so you can't always say, if you have a countable set, you can't say choose the smallest one or something like that. They might be the numbers 1 over n or something like that, and you can't choose the smallest one. So you can't. So a figure like this might, lead to say, okay, take a proof. We'll take the smallest guy in spec of alpha, the second smallest, so on. You can't do that, but that's okay. But the main thing is you can see that it's not continuous. It's countable, and choosing spec, it sounds like spectrum or special, but anyway, it's better than A sub alpha for the purposes of exposition to the user community that we have in mind here. Now the caption also is redundant. This is for the people who read only the captions and don't read through the paragraphs. Right now, this is a technique that everyone knows from Scientific American and various other scientific journals, where National Geographic and so on as well. You know, where you can browse the articles and look at just the captions. And so, in fact, in National Geographic, they have quite elaborate captions. Sometimes that goes on more, sometimes longer than the article itself, because they want to make sure everybody reads the good stuff. Yeah. But okay, so he's the only student who used this idea, but it's something worth emphasizing because I hadn't mentioned it before. So this is the caption providing more information. It doesn't just say figure A. It's got a little story there going on, and there's this convention in his picture that he draws. He has an alpha, and then he has spec of alpha on another line, and now he gives figure B, which is the corresponding thing, trying to explain the hypothesis that if alpha is unequal B, then one is in alpha is in spec B or the other, and I amplified the caption a little bit here when I read it, and I made another change that David might or might not agree with me on. I'll tell you about it now. I used alpha and alpha bar instead of alpha and beta, and the reason is that later on in his proof he had so gotten into the use of alpha in his thing that finally when he does the diagonalization, he's sitting there with a set alpha bar and an n bar and t bar corresponding to it, and those are well, n and t correspond to alpha, n bar and t bar correspond to alpha bar, and so he's actually applying this hypothesis with alpha bar instead of with, and beta never appears later on in the argument. So I thought it might be wise to introduce alpha bar right from the beginning, so that when you're applying the hypothesis, you've already got the figure that shows it. On the other hand, alpha bar, somebody might say, what is this? Is this minus alpha? Is this the complement of alpha? Does this have some semantics, or is it just an arbitrary other real number? And so I in order to diffuse that ambiguity, I added two words here. I said for two reals, alpha. Whoops. For any, Phyllis put it in the wrong place. It should be for any two reals, alpha unequal alpha bar. But I think David had only written for any alpha unequal beta, and I said any two reals alpha, just to sort of give the feeling there that they weren't related in any other way except being different. But I'm not sure which way to go on that, but I did make that change here. I had to report it. Now the way he's done it now, though, he has a color code. So the alpha dots are like figure A in red, and the beta dots are like figure B in blue, or like figure A in blue. And there's a problem when the blue and red want to be on the top of each other. So maybe, I don't know what the right solution here is. I used X's and dots in order to get it black and white, but he has a convention. But the main point is now that he's searching for a graphic that will be a visualization of the mapping from alpha to spec of alpha and the condition that we have between spec of alpha and spec of beta. Then he goes and gives the figure, which says all but a finite number map S into the entire set of reals. So here he has a set S indicated, and S is being mapped by F1 onto all reals, and F2 into all reals, F3 into just a spotty set here, and so we're somehow indicating that most of these come out to be all of the whole set of reals. Now he goes on and gives before we go on to prove Sierpinski's theorem, let's take a look at a lemma, which we will state here without proof. The lemma says that there is a one-to-one correspondence and so on. Now, Now he illustrates this lemma by giving another correspondence to two-way, the two arrows here, between something which he illustrates graphically, and he's got this idea of the N's and the T's, where the N's are on a line and the T's are on a plane. Now, if he had worked together with Pang, he would have given this as a single graph where you have N and T coordinates. In other words, given so that Pang's idea, having the sequence of ordered pairs, means that you really are just giving points on a graph, which would even be a better visual for this thing, because it's going to turn out that those are the things that work out really nicely in the proof. And I imagine you might even have converged on that if you had more time to work on this. But that's so. Anyway, we have a visual here that shows the correspondence, and in the improved version with Pang, it would just correspond that to a set of some graph of points. And the projections and things would be visual, could be done then. Now, step 1, step 2, step 3, and so on. And he's got these things growing. So he starts out with alpha, and he's got various points in spec of alpha, alpha 1, alpha 2, alpha 3, which each have their own little graph that go with them. You see, and this is how the L sequence is being constructed. Now, you see how these images are remaining consistent and nesting on each other to build a bigger thing. Now, the same idea was used very effectively by similar idea. I mean, same concept somehow was used very effectively by Peter Nauer and Nicholas Wirth when they wrote the original write-ups on Algol 60 and on Pascal. They would start out and they would define the syntax of the language, but they would also give examples of everything. So they'd give an example of an identifier, and they would give an example of a constant, and they would give an example of a simple expression, and they'd give an example of a Boolean expression, and so on. And these examples built on each other. And so as you go through the Algol report, you would be seeing a story that was sort of being told, the subsidiary to the main one, and you could follow the characters as they were developing. The examples fed together and formed components. The expressions that you were building were from simpler parts that you had already understood the simpler parts. And he's doing this visually now in these diagrams. And so then we have, going through the construction, we're getting the big step 4 here, which goes from which goes to f of s, some assumption about the theorem, and now the grand climax is steps 5, 6, 7, 8, 9, and 10. It takes us back here where we get our contradiction, and you can actually follow the thing. You go through the arguments. You got f of s. These are the sets that these are the images that have missing points. Then you can go from these to actually select missing points. And now we would do this actually with Pang's idea. We would simplify this, because when f1 is missing a point, then we get a 1 comma t is that point that's missing, and so we would get a graph that was just a subset of the complement of this image here. And then that would take us up through 6 to spec of alpha and spec of alpha and spec of alpha is an arbitrary element that we're trying to prove is not in S. And then we have spec of alpha bar, which then we can use to get the contradiction, and we can go back down and we can get down to here. Okay, so that's anyway, so it was possible to make a visual story out of this proof, following the proof as it was, and it was innovative, but using basic ideas that generalize, I think, when you're doing. Now this is something that you use most often that I use most often in making a lecture, because I usually don't have enough of a budget to make a lot of illustrations in the articles that I write, And certainly I don't have color. But when I'm making slides for an overhead projector, I've got more than 4 colors. I got, you know, and make a lot of diagrams, and so I can wave my hands and show to people. And I don't, you know, Lamport might or might not talk about giving a lecture here, but I know one of his axioms is never try to give a proof in front of an audience. And rarely does it work. But if you have some pictures, they can get the idea that, yes, they could understand it if they go back and in a quiet room and think about it. So this is a good example of the kind of techniques that you use for your ordinary papers that have to go into dry journals that don't, you know, you don't have much room for illustrations. You still use this technique a lot in communicating to people when you give a presentation orally. And it would be nice if we could afford this in all the journals and if people had the time to do it. By the way, my experience is that the amount of work involved in getting a paper published and preparing it and getting it all finished is proportional to the cube of the number of illustrations in the paper. And so when I had something like that, line breaking into, you know, paragraphs and things like that I showed you last time, then that pretty much did me in for a couple of months. Any other work that I was supposed to get out the door was impossible during that time. Okay. Any questions on this? Come on. No. You got to have something to say. Okay, so now you can say, when do you get your papers back? Yes, okay. After class. We decided not to give them to you before class because then you wouldn't be listening at all. But I think that if you look at if you read this handout with the solutions, now that you're a little motivated after having done it yourself, that'll complete the amount of learning that I wanted to get across there. Okay. Now let's see. Looking ahead, I've got. Okay, I'll say a few more things about illustrations of algorithms. I didn't have time to finish everything on Wednesday. I'll base all of this on Volume 3 of The Art of Computer Programming, and then I'll have some other introduction of things we're going to talk about next week. So Volume 3 of The Art of Computer Programming. On the frontispiece here, I have actually it doesn't. I think maybe I explain it in the text somewhere, but this illustration, I had to prepare it on a CalComp plotter. This was done in the late 60s and didn't have a way to do types in it. But this is a mathematically interesting illustration. It illustrates a hash method based on the golden ratio. And if you look at it from the bottom to the top, this is you can imagine putting things into an array. And the first one goes in at position 0.618 of the total array. Now this is the golden mean of the Greeks, the golden ratio that's supposedly used in a lot of ancient architecture. And if you put the next one, it goes into the fractional part of 2 times the golden ratio, which is 0.6 times 2 is 1.2. No, wait, is that right? Yeah, but it's so it's actually going in here. It's not at the golden ratio square, but at 2 times the golden ratio. This one goes in here, but this number divides the first part into two parts, which are divided in the golden ratio, and the third one goes into fractional part of 3 times phi, which is over here. And that divides its sub-interval into 2 parts. One is the golden ratio, and one is the. In other words, this was 0.6, and it's now being divided into 0.3 and point what? What is it? 0.4, isn't it? The complement. 0.4 and 0.2, roughly. And then anyway, each term, as you add in each point, it's the n times the golden ratio. I'll take the fractional part. And the interesting theorem about these is that every time you add a new point, it falls in one of the largest remaining intervals, and it divides that interval in the golden ratio. So these points stay very far apart from each other, and this is useful in hashing because you don't want things to cluster up. And so if you happen to have sequential keys and you use a golden ratio for hashing, then this spreads them out in the table. So that was used as a illustration there, and I think I did mention it when I got into hashing, that it was in the frontispiece. Now here's an example on page 8 that is another illustration of my philosophy of trying to give a long illustration of something that prints a lot of the rules. This one was fun to make up. The exercise is going to be to design. I mean, this is a exercise, a 33 level exercise, which is supposed to take a while to do, but is to design a way of handling inside a computer the way that librarians alphabetize things in the card catalogs. And actually the rules for alphabetical order in a library card catalog are somewhat hilarious, and you have to, but if you want to find something in a library, you have to ask the reference librarian or know these rules. And so I was saying, how could you do this inside a computer if you're going to do this is a book on sorting, and I'm saying, how could a computer sort cards into the order the way the librarians do? And so these are in alphabetical order here. And the first cards, for example, is alphabetized under A, C, because you ignore foreign royalty except British. This is one of the first rules in things. So if it's the Royal Society of London, it's under R. But if it's the Royal Society of Turin or Linz, Rome here, it's under A for Academy. Okay, now here we get 1812 is alphabetized under A because this is in German language, so you spell it out 1812. The next one, it says treat apostrophe as a space in French, and so the D de histoire here is before des because it's a space in French. Okay, you have to ignore accents on letters. Brown, Mrs. Does not count in the alphabetization, so J comes before John. So then there's other rules like this. John Brown of Boston, mathematician. You have dates then come in, and you have works about somebody following works by, and all this is going on. You see the idea here that some of these are, here's another 1812 overture coming in here as D suite. You ignore articles at the beginning and so on, and Al in Arabic names gets out, and respell labor without the U. I got John McCarthy in here. John was interested to know that he was in my book, but he found out he was only as data, not as content. But McCarthy comes before machine. Okay, and saint st equals saint even in German. Okay, so anyway, now, but my main idea here was in order to illustrate the problems of doing sorting into alphabetical order, you will need to know what the computer program really has to do. And so I made up a detailed example like this, which would illustrate the problem of the exercise, and then the answer to the exercise, as you can guess, somebody who has written BibTeX, for example, would be to keep to have a way to have the letters here that appear in the card catalog, and then you have a secret key inside that you use for sorting, and those are all, and the answer explains that sort of thing. Okay, so so all these little rules were interested here, and it says most of these rules are subject to certain exceptions, and there are many other rules not illustrated here. But that's the main idea of that I wanted to get at, is making an example that is interesting to read, but also detailed enough. Now I tend to like detail myself. I'm not sure if this goes over with everybody, but the book seems to sell all right. So. Yeah. Now here's another illustration I made about, which I worked hard on. This is, I had to arrange the 24 permutations of, to illustrate the idea of, this is a section called inversions of a permutation, and every time you interchange two adjacent elements of permutation, the number of inversions changes by +1 or -1. And this is at the top you have 1, 2, 3, 4 has no inversions. The inversions are pairs that are out of order, and at the bottom it has no inversions. And every time you go through one of the lines here, you drop by 1 inversion. And so you can visualize all 24 permutations by their inversion this way. Now, in order to get this diagram, though, I knew that it formed a truncated octahedron, but I had to rotate it to a position where these things weren't going to interfere with each other. And so I made a geometric model inside the computer, and I had to work with a Calcom plotter here. We had no graphics in those days, and so I rotated it and turned it around, and then plotted it many different angles until I found the one that would look readable from here. So that took quite a few experiments in order to get that illustration. Now let's see, I'm giving examples of algorithms mostly, though. Let's see, where do we have? So here's an example of an algorithm where the construction proceeds as follows. And so step by step we go through and we insert and we do things. So I'm talking about a construction here. Best way I know to explain that construction is showing a small example step by step so that you can see the way it works. There's, let's see now, next. Sometimes there was just a chart that showed a construction. Let's see now. Table of numbers goes in here. Here's a table. Now, sometimes numerical tables are considered unenlightening because you have to look at the numbers. You have to really love numbers in order to appreciate a numeric table. Well, in this case, I think you can get the idea that we have these numbers are getting very close to 2. But they oscillate, and they go up and down around 2, and they sort of oscillate. And the period is actually pi, I think. Actually every 3.14 it changes sign. Although you can't even tell the difference by the time here. These are unusual polynomials. I wanted to show how fast they converge to 2, and you can't do that graphically because you have to see the numbers. I mean, they're just so close to 2, they'd all just look like 2 if you plotted them, I think. So and then the reason for this is given. Now let's see. This is. It's always helpful for some classes of readers to have some connection with games, and so I have playing cards on the left and chess on the right. Suck people into doing the exercises. Not everybody loves these games, but. A lot of people do. Now here's an example of an algorithm where I'm doing another step-by-step thing, and it's just an algorithm that builds two arrays, and so you see the algorithm as it's proceeding, and so you have to and I worked it out so that it'd be on the facing page, the algorithm and this chart. Oh, something I forgot to mention on Wednesday when we showed I was showing examples of this breaking a paragraph into lines, and there was a case where I couldn't get the two. I had 2 paragraphs that were typeset. One is typeset by brand X, and one is by brand Y. And naturally, you'd like to have them together so that you can see them both and compare the 2. But there was a lot of other text that had to go between them, and so you couldn't have them on facing pages. But you could still arrange that one was on the left-hand page and another was on a right-hand page. And then you can have any number of pages in between those, and you can still compare the 2 as long as they're on opposite pages like that. And Michael Platz taught me that idea of being able to have things. So if you had something that you have to, that there's no room to get them on facing pages, but you can still get it like this, and they're still facing pages as far as the person has to compare is concerned. It's not you don't get to give people little cards to carry and overlap or something like that, with which would be the optimum way. But this is pretty good second choice. Again, an illustration of an algorithm step by step by giving a specific instance of the algorithm as to what happens. A person can read through these and work them out with a little piece of paper, but the algorithms are inherently not trivial. So I believe this is the best way known to present them. Here's a symbolic where it shows the possible places where where the next step could put number 15 into the thing. So, okay. Now, in the main part of the text on sorting, I carried through an example of 16 keys that would be sorted by 20 different ways. And so I got these keys, and you almost get to know them by heart if you keep reading this book. You can quote them each one has a somewhat different graphic that goes that indicates how it works. So when you sort them by straight insertion, there's this idea of where you're going to insert the next key. And so 87 gets inserted before 503, and then you get to the next line, and 512 pops up, and it has to be inserted after 503, and then 61 before 87, and so on. And then there's a two-way insertion algorithm described here. Then there's shell sort, the diminishing increment sort, where you compare things that are far apart, and you swap them if they're out of order. And so that's illustrated on those same 16 keys with a different set of increments you got over here. List insertion is strange. I don't know what to do about the graphic there, but that was it. Then we had the bubble sort. Here's bubble sort on the keys, and here we put the bubbling up, and you got the cocktail shaker version of the bubble sort, and and you got Batcher's method, which has this kind of another kind of comparison scheme and a geometrical interpretation by corresponding to folding paper that's illustrated on the same page. So as far as I know, here's the radix exchange, a quick sort. This is quick sort, and here I use boldface to illustrate the key in which I'm doing the partitioning. No, the keys, the boundaries of the subfile in which I'm partitioning, I guess. That one of those is also the key on which it's doing the partition. Here it is, the quick sort. Now here's the boundaries. This is fine print, but it shows the idea of quick sort. We tried to get that in there. Then for radix exchange sorting, it was something where you used the binary values of the keys, so I had to give them actually an octal here. Binary would have taken too much space, so I gave the same keys in octal, which you can use to see the pattern of bits in the keys. It was a binary-based method. Okay, so anyway, carrying through an example of the same thing sorted in different ways. I helped to tie it together, but also illustrated the different sorting methods. Here's a method of sorting those keys where you pretend it's a tennis tournament and the winners go to the top and things like that. All right. Now, next week I want to talk about two things. First of all, on Monday, my plan is to discuss getting quotations to use at the beginning or end of chapters. This I think is actually one of the most fun parts of all technical writing, so I'm looking forward to Monday myself. Then on Wednesday and Friday, I'm going to talk about my fights with copy editors, and to give you a preview of that, I don't know. I got. According to Dennis Flanagan, I was one of the only authors who ever was able to see page proofs of his article because I was so upset with the way the thing first came out. And so I will show you some of the things that the ways they ripped off my writing when I sent it into Scientific American and some of the sequels to it. And you'll see that I was wrong sometimes, but most of the time there's issues in there which are going to arise and also in your own writing. So we'll see this. So now Scientific American was known for heavy rewriting of articles that were submitted to it by scientists. And some people would say, if any of your words survive, this is really incredible. So I decided before I sent my article in, I was going to be the first author whose article would not be touched by Scientific American, and I would send them something that they would accept, sort of word for word as it was. And so I was going to epitomize the Scientific American style and so on, and I wrote in. Well, what I got back was completely different from what I wrote, of course. And then these are the and then these red marks here are things that I felt absolutely had to be changed before we went into print and over and over here. And I would still much rather reprint the way I wrote it, but we'll see, you'll see that story on Wednesday and Friday. And some other, I had a call from ACM copy editor today, and we had a long discussion about whether data is singular or plural. So and she sent, yes, very shocking. Yes, and I'll tell you about that also. And she says a letter is coming in the mail. So.